First part, we're going to find the mass of the black hole. The two formulas are Newton's second law, as always, and universal gravitation, which is the force between two masses. There's no experiment. The result is 10 to the power of 34, which is really big amount, but it's reasonable because we are dealing with black hole, which is a very, very heavy object. And this is the detail of that universal gravitational force. I literally put that in the code. And here's the surrounding systems and surroundings diagram. We only have black hole and star on our system, and there's no such surroundings around those two. No experiment again. The code is already given, so I captured some of them to show you what I actually used. Star mass of the star, and used a day, 24 hours, 60 minutes, 60 seconds for the time period. Here's how I got the net force, because the velocities were already given, so I just got the momentum, change of momentum, and change of momentum divided by change of time, which is net force by the definition of Newton's second law. And that's actually the answer of what does it mean question later on. Here's how I got the result. As you can see, I got a whole bunch of numbers, but those numbers were precise enough, so I got the mean of those sequence of numbers. And it was reasonable. The number were, oh yeah, 1.54, 10 to the 34. And here's the regular code execution. As you can see, the yellow, the orange arrow is the force, and the other two are parallel and perpendicular component. No experiments again. There's no such similarities and differences. Error, I cannot see any error in there. Again, what does it mean question? There's no difference. The net force and the rate of change of momentum is just the same by the definition of Newton's second law. Part two, get the initial velocity of our ship to, escape from the orbit of black hole. There are two additional formulas, update formula that we have already used in the lab 1, and circular motion formula, which is going to be, well, here's the result. The velocity is supposed to be 1.8 10 to the power of 7, but that's not so important because that's just a value. Here's the formula for circular motion, mv squared over r. That is important to get the velocity. Here's the systems and surroundings, black hole, planet, and ship. That's all. Those three are in the system, and there's no such surroundings around them, and no experiment again. The mass, the result from the part 1 and all the other codes are already given, so I will go through these slides faster. All right, here's the code execution of it. That speed is just, I just got it. I just got a speed that actually makes sense in the diagram, as you can see here. The pink is not going back to the black hole. Similarities and differences, no such stuff. There's no error. I cannot really find any errors because the velocity is reasonable and it looks clear. What if question? Initial velocity to enter the orbit around the black hole. For answering this, I've used circular motion formula, and on the left-hand side and on the right-hand side, universal gravitational formula. Because universal gravitational formula is actually the force amount you can find between two objects, and then circular formula is the force amount required to be in the circular motion. So if I link those two, I can find the, the optimal velocity to be in the orbit. And if you're trying to use that formula like that, you can see something interesting in the diagram. As you can see, orbit there. Precise, it was very precise. The massive black hole in the part one was very consistent, and the speed was reasonable because it was less than the speed of light. That's all.